Welcome friends to my YouTube channel Sommo Physics. On yesterday's lecture I told about Carnot theorem and its proof. Okay, and I derive two parts of Carnot theorem. That first one is that the efficiency of all reversible engines working between same two temperature limits are same. Now the second part I also prove that no engine is more efficient than a reversible engine. Now in today's lecture I shall discuss about an important diagram which is known as the temperature entropy diagram, which is known as the temperature entropy diagram. What is it? Now we all know about indicator diagram. We all know that it is a diagram which is made up of two thermodynamic variables, any two thermodynamic variables. For example, one is PV and another is TS. So suppose this is the temperature entropy diagram. Okay, this axis is T and this is S. So the nature of the temperature entropy diagram is a rectangle. Okay, the shape is rectangle. Say this is T1 and T2. Say this is S1. Say this is S2. This is say A, B, C, D, E, F. Okay, so here the TS diagram is simply a rectangle on which heat is absorbed along AB. That means isothermal expansion takes place along AB and isothermal compression takes place along DC. Okay, so working substance undergoes isothermal expansion. Isothermal expansion along AB. Okay, at temperature T1. That means it absorbs heat from source at temperature T1, and we all know the condition here. Here the work done by the gas or the working substance is equal to the heat absorbed from source. Okay, so in this case the work done by the working substance this must be equal to heat absorbed from source. Heat absorbed from source. Okay, so if say Q1 represents the amount of heat absorbed, then this is nothing but the area of the Carnot cycle, that is area under ABFE. Okay, area under ABFE. Now what is the area under ABFE? That means AB multiplied by BF, say this. Now what is my AB? AB is this, simply EF. Okay, and what is EF? S2 minus S1. S2 minus S1. And what is BF? That is simply T1. So this is the heat absorbed from the source, which is represented by the area ABFE. That is this area, this total area. Okay, so this is the heat absorbed from source. Now what will be the amount of heat rejected to sink at temperature T2? Okay, what would be the amount of heat rejected to sink at temperature T2? So let us find out that. Amount of heat rejected to sink at temperature T2. This simply, if you call it Q2, then Q2 will be what? Area under DCEF. Area under DCEF. So what will be it? That is CD multiplied by DF. So what will be CD? That is S2 minus S1, and this is simply DF means T2. Okay, so we have got both the expressions, that is amount of heat absorbed from source and amount of heat rejected to sink. Now we can easily find out the amount of heat which is converted to work. So what will be it? The amount of heat which is converted to work. Okay, so heat converted to work, if we call it W, then we can know the formula Q1 minus Q2. So my Q1 will be what? S2 minus S1 into T1, and Q2 will be what? S2 minus S1 into T2. So if you take it common, that means S2 minus S1 common. So what we get? T1 minus T2. Okay. Now we all know the formula of efficiency. We know the formula of efficiency, that is total work done by amount of heat absorbed. Okay. So what will be? Oh, sorry. Why I forgot to tell one thing, that if you subtract this area from the entire one, then this portion will only remain. Okay. So the amount of work, amount of heat which is converted to work can be represented by the square area, that is area under ABCD. Area under ABCD. Okay, so if you subtract this portion from the entire, then you will get the ABCD section, that is the area under the Carnot cycle represents the amount of work or amount of heat which is converted to work. This is the significance. So if you get back to the efficiency, then you put W equals to S2 minus S1 into T1 minus T2, and what will be Q1? My Q1 will be S2 minus S1 into T1. Okay. So what will be the result? This cancels, 1 minus T2 upon T1. So thus we see that by using temperature entropy diagram, the efficiency of the engine becomes exactly same as we obtained in Carnot cycle. Okay, so from here we can easily conclude that PV and TS diagram are identical. PV and TS diagram are identical. Okay, PV and TS diagram are identical. So this is the case, and thus we see that if we find out the efficiency of a reversible Carnot engine by using temperature entropy diagram, then we get the same expression as obtained in PV diagram. So from which we can easily conclude that PV and TS diagram are identical. Now one question, that what is the significance of temperature entropy diagram? That I told that the area of the Carnot cycle ABCD represents the amount of heat which is converted to work. This is the simple interpretation of temperature entropy diagram. Okay. So this is the simple interpretation, that the area under the Carnot cycle represents the amount of heat available converted to work. Okay. So this is the significance, that area under the Carnot cycle represents the heat that is converted to work, that is converted to work. Okay, so this is the simple significance of temperature entropy diagram. So this is the significance of TS diagram. Okay, this is the significance of temperature entropy diagram. Now one thing I want to tell in this video, that what are the changes in entropy for gases. Okay, I have to tell it. So in today's lecture I shall only do the perfect gas. In case of a real gas and gas mixture, that I will do in my next class. So it is the entropy change for an ideal gas. Okay, entropy change for an ideal gas. At first you have to consider the simple case, that is ideal gas. Okay, now we know that from first law of thermodynamics, that is dq, this simply equals to du plus p dv. Okay, now if you divide this term by t, say, then what will get? Du upon t plus p by t dv. Now we all know these two relations. Du, this is equals to cv dt, and for perfect gas pv equal to RT. We have to use these relations, and dq by t is nothing but ds. Okay, and here you substitute cv dt, so what we get? Cv into dt upon t. So here you put p by t means r by v, that is r dv upon v. Okay, so if you integrate this expression within the limits s1 to s2, and you integrate it within the limits t1 to t2, and this you do for v1 to v2, then what we get? We get s2 minus s1, this equals to cv ln t2 upon t1 plus r ln v2 upon v1. Okay, so this is the general expression for change in entropy for a perfect gas. Okay, now you can calculate this change in entropy for a perfect gas under uh, all conditions. Suppose but you have to do up some simplification, so that we will tell in my next class. Okay, but till now I shall derive the general formula for entropy change for a perfect gas. Okay, so this represents the general formula for, say, delta S for an ideal gas. For an ideal gas. Okay, the marker is almost finished, so I have to finish this video here. Okay, so up to this, in this class I shall derive the change in entropy for an ideal gas, and in my next lecture I will do it for perfect gas and gas mixture, and also I do it in a more. Also I will do this for different cases, that is for isothermal, adiabatic, or isobaric, isochoric processes. I will extend it. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends. Okay, thank you.